शारदे माँ, हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ। मुनियों ने समझी, गुणियों ने जानी, वेदों की भाषा, पुराणों की वाणी। मुनियों ने समझी, गुणियों ने जानी, वेदों की भाषा, पुराणों की वाणी। हम भी तो समझे, हम भी तो जाने, हम भी तो समझे, हम भी तो जाने, विद्या का हमको अधिकार दे माँ। हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ।
We request Mr. Deepak Mathur, the chief guest, Dr. Sibaraj Pillai, the guest of honor, and the other conference dignitaries to elevate the conference with their presence on the dais, please. We also take this moment to thank our patrons, Shri Sunilji Raisoni, Chairman, Raisoni Group of Institution, Srimati Shobha Raisoni, and Mr. Shreyas Raisoni, Executive Director, RGI. So, to add to this special day, ladies and gentlemen, today we see a dais of excellence with two renowned personalities who hold a predominant name in the field of engineering and technology. It's our honor to welcome our chief guest of today's conference, Mr. Deepak Mathur, the Vice President of Member and Geographic Activities IEEE and the former Director IEEE Region 10. We welcome the guest of honor, Dr. Sibraj Pillai, Professor Electrical Engineering, IIT Bombay. I request Director Sir to welcome Mr. Deepak Mathur. I request Dr. Mahendra Gaikwad sir to welcome Dr. Sibaraj Pillai. I request Lakshman Thakre sir to welcome the Honorary Chair of the Conference and the Director of GHRC, Dr. Sachin Untawale. Dr. Atul Deshmukh sir to welcome the Organizing Chair of the Conference, Dr. Santosh Jaju sir. I request Dr. Mahendra Gaikwad sir to welcome Dr. Pramod Balke sir, Deputy Director and Dean Academics. Recognizing and appreciating sincere efforts not only uplifts the spirit, but also inspired continued efforts and dedication. I request Director Sir to present the memento to the General Chair of the conference, Dr. Mahendra Gaikwad Sir. Dr. Lakshman Thakre Sir. and Dr. Atul Deshmukh, sir. Thank you, dignitaries, for being gracious enough to join us this morning. IEEE, the world's largest technical professional organization dedicated to advancing technology for the benefit of humanity and the trusted voice for engineering and technology information around the globe. GHRC marks its proud association with IEEE every year through such international conferences, student and faculty chapters. Recent award to mention that we have received IEEE Student Branch's Platinum Affiliate Award for the section. Through platforms like this, we not only celebrate our association, but also create a space where knowledge meets innovation, young minds connect with global advancements that are shaping our future. With that note, we accelerate to the next proceedings, ladies and gentlemen. Every conference invites an inquisitive preamble to unfold several ideas, creation, research, and development, which is an integral part of it. So we now request Dr. Atul Deshmukh, General Chair of the conference, to present the preamble.
Chief guest, Mr. Deepak Mathur, IEEE 2024 Vice President MGA and past IEEE Region 10 Director. Guest of honor, Dr. Sibiraj Pillai, Professor Electrical Engineering, Department, IIT Bombay. Honorable Sri Sunilji Raisoni, Chairman RGI, Sri Sheyasji Raisoni, Executive Director RGI in his absence. Honorary Chair and Director of the Institute, Dr. Sachin Untawale sir, Dr. Santosh Jaju, Organizing Chair and Dean R&D, Dr. Pramod Walke, Deputy Director and Dean Academics. My counterpart, Dr. Mahendra Gaikwad and Dr. Lakshman Thakre, General Chair of the conference. Session Chair, keynote speakers, delegates, authors, students and dear participants. Good morning and a warm welcome to each one of you. It is a matter of pride privilege for me to present the preamble of 12th IEEE International Conference on Emerging Trends in Engineering and Technology, Signal and Information Processing, ICETET SIP-25, organized by GHRCE College of Engineering, Nagpur. This flagship conference hosted by Department of Electronics Engineering, Department of Electronics and Telecommunication, and Department of Information Technology, GHRCE College of Engineering, Nagpur, technically sponsored by IEEE and co-sponsored by IEEE Bombay section. GHRCE College of Engineering is a converge of innovation, research, and academic excellence. Over the years, ICETET SIP has emerged as a strong academic platform that fosters the exchange of novel ideas, collaborative learning, and meaningful discussion across a wide spectrum of engineering discipline, with a special focus on signal and information processing. This year, ICETET SIP received an overwhelming response from researchers across India and abroad, with a total of 1041 papers submitted. Following a rigorous peer review process, 174 papers were selected for presentation and publication, resulting in an acceptance rate of 16%. The conference saw participation not only from the India, but also from countries such as USA, Indonesia, China. Truly reflects the global relevance and outreach of iState SIP. This year, we are proud to host a wide array of sessions with two keynote addresses by Dr. Sibiraj Pillai, Professor Electrical Engineering, IIT Bombay, and Paulo Maconcini, University of Sao Paulo, Brazil. Total 19 parallel technical tracks for paper presentation covering emerging domains such as AI, ML, IoT, VLSI, biomedical, communication system, data science, cybersecurity, and more. We are immensely honored to have with us today Mr. Deepak Mathur, our esteemed chief guest, whose visionary leadership continues to inspire professionals in the field of technology, and Dr. Sibiraj Pillai, guest of honor and a distinguished academician from IIT Bombay, whose presence add great academic values to this forum. On behalf of organizing committee, I express my sincere thanks to IEEE Bombay section, all technical reviewers, publication partners, session chairs, track coordinators, and student volunteers whose dedicated efforts have made this event possible. We are also grateful to our honorable patron, Sri Sunil Ji Raisoni, for his constant encouragement, and honorary chair and director of the institute, Dr. Sachin Untwale sir, for his unwavering support in our pursuit of academic excellence. To all the participants, I encourage you to fully engage with the technical session, interact with fellow researchers, explore possibilities of collaboration, and absorb new ideas. Let ICETET SIP-25 not just be a conference, but a celebration of innovation, learning, and academic excellence. With this, I once again welcome you all and wish this conference great success. Thank you all.
Thank you, sir. Research and development forms the very heartbeat of an educational institution, driving innovation, nurturing intellects, and shaping its journey towards academic excellence and societal impact as a whole. So now it's time to hear from the Deputy Director and Dean R&D and the organizing chair of the conference, Dr. Santosh Jaju sir, on his address.
Good morning. Dignitaries on the dais, Chief Guest of the function, Shri Deepak Ji Mathur, Past Director, IEEE Region 10, Guest of Honor, Dr. C.B. Raj Pillai sir, Professor of Electrical Engineering, IIT Bombay, Honorary Chair and Director GHRCE, Dr. Sachin Untwale sir, General Chairs, Dr. Atul Deshmukh, Dr. Lakshman Thakre, and Dr. Mahendra Gaikwad, Deans, Heads of Departments, faculty members, and dear participants, offline and online. Good morning. I welcome you all for the inaugural ceremony of this 12th International Conference on Emerging Trends in Engineering and Technology, with a special focus on signal and information processing, ICETET SIP 2025. Organized by Department of Electronics and Telecommunication Engineering, Electronics Engineering and Information Technology, and technically sponsored by IEEE and technically co-sponsored by IEEE Bombay section. This 12th edition itself shows the consistency in organizing this conference and providing the platform to the researchers. As a Dean Research and Development, I would like to brief you about research and development accomplishments and activities of the Institute. With effective R&D policies and norms in place and the support from visionary management, the intellectual capital of Institute is noteworthy. Institute has more than 6,800 publications in reputed journals and conferences with citation count more than 25,000. With 235 books and book chapters, 450 plus copyrights, 500 plus patents being filed, 100 plus patents being granted, out of which 12 are international patents, and several technologies being transferred to the industries and are in the process of commercialization. Institute is approved research center for doctoral studies, wherein more than 50 PhD scholars are pursuing and 170 plus PhDs have been awarded. We have received research and development grants worth 45 crore plus for research projects from various government agencies like Department of Science and Technology, AICTE, UGC, and even professional societies like IEEE, IEI, to name a few. Apart from this, industries have spent 14.2 crores on 485 projects being carried out by faculty and students together. We have organized 19 PhD colloquias, 65 national and international conferences being indexed by various international indexing agencies like Springer, IEEE, American Institute of Physics, to name a few. We have established 20 Center of Excellences in thrust areas such as biomedical engineering, AI/ML, IoT, smart city, energy, AR/VR. Apart from incubation center, pre-incubation facility, IPR cell, research park. GHRC has taken a significant step to launch its nano satellite with the involvement of students and faculties as GHRC SAT. I must congratulate Department of Electronics and Telecommunication Engineering Electronics Engineering and Information Technology for organizing this IEEE ICETET SIP 2025. I am sure that this conference shall lead and benefit the participants and shall update their knowledge base. Thank you.
Thank you, sir. It's now time for a welcome address, and for which I request Dr. Sachin Undwale, sir, the honorary chair of the conference, to present his welcome address.
Thank you, Sindhuban. Good morning, all of you. Dignitaries on the dais, the chief guest of today's event, Mr. Deepak Mathur, sir, past director, IEEE Region 10, guest of honor and a keynote speaker, Dr. C.B. Raj Pillai, Professor, Electrical Engineering, IIT Bombay, organizing chairs, Deputy Director and Dean, Academic, Dr. Pramod Walke, Deputy Director and Dean of R&D, Dr. Santosh Jaju, the three general chairs of the three departments, Dr. Atul Deshmukh, Dr. Lakshman Thakre, Dr. Mahendra Gaikwad, dignitaries of the dais, deans, heads of the department, and my dear participants, including the students. On behalf of GH Raisoni College of Engineering and on my personal behalf, I welcome you to this 12th in series International Conference on Emerging Trends in Engineering and Technology, Signal and Information Processing 2025. It is an honor for me to be here in front of you because I am sharing the dais with two eminent personalities who have accepted our invitation to grace this occasion. Thank you, Mathur sir. Thank you, Pillai sir, for joining us for this conference. As very rightly said by Dr. Santosh Jaju, that this is the 12th conference being organized in series. This reflects the following of GHRC with the United Nations 17 Sustainable Development Goals. We at GHRC focus on two most important concepts that are required for today's working. First is innovations, and second is sustainability. And here, I'm standing in front of you, and I can say that we are following 3 SDGs in this particular conference hall. The first in the field and actually taking the experience what is required, that is passing us this information through these conferences to the students who are the major stakeholders of this institution. So SDG 4 has been taken care of. SDG 17 is organizing events that are related to the theme of the organization. And the theme of this institution is to conduct various events, various conferences, various training programs for not only upgrading the faculty members, but also for upgradation of the students. And therefore, this SDG 17 is also met with. And the third most important that I can see here is SDG 5, that is gender equality. So a portion of the institution, almost 50% of the stakeholders in these institutions are female. And therefore, at GHRC, we also follow SDG 5. The rest of the SDGs are also being tried to meet with. However, this is a dream, and by 2030, probably we'll be able to reach to all the SDGs that are being issued by the United Nations. The second most important thing is innovation. Sir, as it has been enlisted that we have filed many patents, and almost 128 patents have been granted to the institution, not only to the institution's technology, but also to the faculty members and the students, those who have filed the applications. And for the information of all present here, almost 50% of the patents, not 50%, almost 40 patents out of 120, 130 are being commercialized for the benefit of the society. And that is what is the basic goal in terms of innovation, in terms of the intellectual property. And I extremely thank IEEE for helping us in conducting such events, wherein the conferences and the publications that the faculty make are extremely useful in carrying out research in the field, not only of electronics, but interdisciplinary field of engineering as well as management. So I please convey my thanks to the IEEE fraternity for permitting us in organizing such conferences. Sir, we have organized 12, this is the 12th one. Out of these 12, we have conducted 2 in Japan, 1 in Mauritius, and 1 we have jointly done with BITS. Our next plan is to conduct one of the IEEE conference. We tried for it for Sri Lanka. However, due to some modalities, it was not approved by IEEE. I request honorable members of IEEE that kindly help us, advise us in conducting a joint conference somewhere outside the country, say Malaysia or Singapore, or any of the proposals that we submit to your office. I request on behalf of GHRCE to help us, advise us for conducting such conference. To end my welcome address, I'd appeal to all the students present here that this is an extremely important platform wherein I am making my faculty competent enough to teach you. So be assured that these sessions, these conferences, those who are in the this is a hybrid conference, so there are many participants from not only from India, but from outside locations, international locations also, and they'll be extremely beneficial. Take advantage of this conference, these sessions, to the maximum extent, and enrich yourself for enriching the students that is expected from all of us teachers. Thank you. Thank you for joining us here. Thank you very much.
Thank you, sir. It gives me mammoth pleasure in introducing the guest of honor of today's event, Dr. Sibiraj Pillai, Professor, Electrical Engineering, IIT Bombay. Dr. Sibiraj Pillai received his PhD degree in Computer Science and Communication Systems from the EPFL, Switzerland in 2007. His research interests include network information theory, feedback communications, cross-layer scheduling, biological information inheritance, and radar signal processing, and many more. We are glad to have with us today on this iconic occasion, sir, and we invite you for your address over this conference.
Good morning, everyone. Yeah, so it's kind of a test run for the longer talk I'm going to give, because I will keep you engaged with my talk anyway. But thank you, everyone from GHRCE College for inviting me to this occasion. And it's a pleasure to be in front of so many people. And maybe I'll have something to say other than the technical talk that I'm going to do in after half an hour or so. Suppose you are in the automobile industry or automobile sector. To the students, I pose a question: do you like to be a driver or an engineer or a mechanic? Let's say driver or a mechanic. Is the question clear? You have a car or you can work with cars. You want to be a driver or a mechanic? Students. So the unfortunate part is that those who like driving, of course, it's very fast paced, it gets to your nerves very quickly. But it's a matter of time before self-driving cars will take your place. That's the stage of AI and associated things that we are in. So I will say it's better to go back to the basics and be also a mechanic, so that you can, driving also, right? You as mechanic knows driving, but driver may not know mechanics at all. And this is the problem of blind use of AI. A lot of people here, the academic community, we are seeing it. Even writing exams is just by AI. And we are not testing the students' intelligence anymore. So that's one advice that I have for people. And that, what I say, has a history also. You have to look 200 years back of the scientific revolution. The main thing was steam engines. And UK, England was the major driver for steam engines because they had coal. They could just dig up how much whatsoever they want. They can just dig and run the machines. So the industry, cotton industry, machine industry, steam engines, all these things became very big in England, and England became a superpower in terms of economy driver. But what has happened is that France and Germany, the mainland European countries, they do not have that kind of resources to dig up. So they did not go after England begging for this coal and associated products. But what they did is very, very remarkable. And for us, India, to keep a track of what has happened then. What they did was they invested in basic science. They got mathematicians, physicists, etc. together to say that, look, can we build an engine from whatever we have instead of digging up coal that we do not have? And turned out that there is a series of people from Carnot to Boltzmann who went after what is the efficiency that we can get. Can we use local resources to produce the efficiency of the British system? So the British engines were running at 15% efficiency, whereas the French eventually, and the Germans eventually went up to the atomic scale, where we have resources of the order of nuclear bombs and hydrogen bombs, etc. All this came out of from that initial technology investment in the start of 1800s. So it's again telling us what we should do, not to copy China, not to copy US and go after what they're doing. But whatever we are doing, can we invest in the basics? Can we spend some time to learn the mechanics of how these things are happening? And then use our creativity to suggest things which will work better for us. Maybe then we will not be intimidated by the Trumps and other people like what's happening now. So that's my suggestion to all of you. Thank you very much. Have a nice conference.
Thank you, sir. Now it's time to hear from the chief guest of today's event, Mr. Deepak Mathur, a distinguished leader within the IEEE community, currently serving as the Vice President of Member and Geographic Activities. His journey within IEEE has been marked by several pivotal roles, showcasing his commitment to advancing technology and fostering community engagement. Previously, he held the position of Director of IEEE Region 10, with nearly 40 years of professional experience in the field of electronics and telecommunication. He has also served as a chairperson of the IEEE India Council, leaving an indelible mark during his term. So we must tell you this, with a recent interview that we have seen, your journey from the base level of a small section engineer to the vice president has been truly inspiring. Ladies and gentlemen, with a huge round of applause, Dr. Deepak Mathur.
So thank you, Dr. Sindhu Panikar. Thank you very much. And I must acknowledge the way you have introduced this particular session. That was really commendable and admirable. So thank you very much. Yeah. Dignitaries on dais, thank you very much, GHRC, for inviting me for this conference. And I really appreciate what Atul Deshmukh told, that this conference is the celebration of innovation and academic excellence. And it should be like that. Nagpur subsection is a matured subsection, and I'm sure in due course of time you are going to be section, and you have to see the parameters for what a subsection is elevated to a section. So I'm sure you are going to get that. And this is the 12th edition of this conference. That shows the consistency and that shows the interest of the organization in organizing conferences. I'll be touching some points which are really important for our members who are involved in academic activities, especially in organizing conferences. Our conferences, we are doing very good conferences. In India, we organize large number of conferences, but we are still lacking in the quality. I'm not referring to any particular conference, but we have to work on the quality of conferences, and we have to raise the standard of quality in each and every conference. And I'm sure I'm in constant touch with the organizers, especially Lakshman Thakre, and I came to know that this conference is taking care of this. That's very good thing. But if we can introduce a session on how to run conferences in each and every conference, so that our next generation volunteers and members are educated. So this is the kind of education we can give during these conferences. How to organize good conferences. For those who wants to organize in future. Number one. Second thing is that we are lacking in elevating ourselves, because our focus is not on that. I have seen that in India we do not have IEEE fellows, and we have to focus on that. That's we should elevate ourselves, and unless we know that what are these recognitions. IEEE fellow is the highest recognition in IEEE or in the world. So you should focus on, especially our researchers, our academicians. You should focus on how to become IEEE fellow. If you are not senior member of IEEE, you should try today only. That is a relatively easy process if you have 10 years of experience and 5 years of some academic excellence or professional excellence. So these two things I would like to advise you all that you should see that how to address that thing. Second thing is that third point is which I would like to tell that our conferences are mainly publication driven conferences. But we have to see that if we can bring some sort of industry driven or balance or including industry at some level in our conferences. I can assure you that the moment you will start engaging industry, you will see that things will change dramatically. I want to see the day when industry comes to the institute like GHRC and they said that, oh, this is our problem. Can your researchers and academicians solve this problem? And this is the two-way process. They will give you problem, they will give you fund, and you will work on those problem. You will do the research, and you will do apply your research and make solution for that. So I want that this kind of the conferences should play a platform for such things. Then coming to that, IEEE is world's largest technical professional organization, advancing technology for the benefit of humanity. This I would like to tell to all students. Whenever you take any project, and even to our professors, that whenever you do any project, see that project is of societal advantage. Can we try to find out what is in the community, what is the problem in the community, and can we solve with the technology? Technology engineering has solution for each and every problem. So our project should be in a such a way that it is not only in the project reports or in the shelf in the type of the prototype, if we can implement at the in our society. So if these things we can keep in mind, then probably we are really serving the society using the technology. And that is what just I wanted to share with you all. I wish this conference a grand success, and you really celebrate innovation and academic excellence. Thank you very much for inviting me and giving me time to do it. Thank you.
Thank you, sir. We desire you continue to shape the future of IEEE's global initiative to greater heights. With that note, all the hard work entails notice, recognition, and acceptance in an ideal platform. What more could that be like this than an ideal platform? So all the hard work in the form of papers and abstracts got together as a digital resource for further proceeding. It's time to unveil the digital resource. I request all the dignitaries to release the conference proceedings. Thank you all. When passion meets responsibility, events like these don't just conclude, they actually leave a lasting impact. And now it's time to acknowledge the collective efforts that made today's conference. I invite Dr. Mahindra Gaikwad, General Chair of the conference, to deliver the vote of thanks.
Good morning to one and all present over here. It is both my privilege and honor to deliver the vote of thanks at the inaugural function of 12th IEEE International Conference on Emerging Trend in Engineering and Technology, Signal and Information Processing, ICETET SIP-25. First and foremost, on behalf of organizing committee and my personal half, I express my sincere gratitude to our esteemed chief guest, Mr. Deepak Mathur, past director of IEEE Region 10 and Vice President, IEEE MGA, for gracing this inaugural function with his presence. Sir, your word of wisdom, technological insight, and encouragement have deeply inspired us, all especially the young minds aspiring to contribute to the innovation and the future technology. I also extremely thankful to the IEEE, particularly the IEEE Bombay section, for their technical sponsorship and the continued support in making this conference a grand success. I also extend my heartfelt gratitude to our guest of honor and keynote speaker, Dr. Sibiraj Pillai, Professor, Department of Electrical Engineering, IIT Bombay, for accepting our invitation and delivering the insightful keynote address. Your presence has highly enriched our understanding and the spark engaging discussion throughout the conference. Your dedication to the research and academia is truly commendable. I would like to extend my sincere appreciation to our esteemed patrons, Mr. Sunil Raisoni, Chairman RGI Group, Mrs. Shobha Raisoni, Trustee RGI Group, Mr. Shresh Raisoni, Executive Director of Raisoni Group of Institutions, for their visionary leadership, encouragement, and unwavering support toward the academic excellence. Your commitment to fostering research and innovation is truly inspiring. My heartfelt thanks to Dr. Sachin Untwale, Honorary Chair of ICETET SIP-25 and the Director of GHRCE College of Engineering, for his continuous encouragement and institutional support. His inspiring leadership laid the strong foundation for successful hosting this prestigious international conference, technically sponsored by the IEEE Bombay section. A special note of appreciation to our organizing chair, Dr. Santosh Jaju, Deputy Director and the Dean R&D, for his outstanding coordination and the dedication. Your commitment played a pivotal role in the successful execution of ICETET SIP-25. I also extend my sincere gratitude to Dr. Pramod Walke, Deputy Director and Dean Academic, for his unwavering support in organizing this event. Special thanks to our General Chair, Dr. Lakshman Thakre, Head of Department of Electronics Engineering, Dr. Ratul Deshmukh, Head of Department of Electronics and Telecommunication Engineering, for their continuous support and untired effort in making this conference a grand success. I express my sincere thanks to the International and the National Advisory Board members of ISTE SIP-25 and to the entire organizing team for their tireless efforts in planning, coordinating, and executing this conference seamlessly. A special mention and a heartfelt appreciation to 350 plus reviewers across India, including the experts from IITs, IIITs, NITs, and other STEM organizations, for their dedicated work in maintaining the quality and the integrity of the conference. Also to our volunteer, technical team, program chair, track coordinator, thank you for your behind the scene efforts that ensure the smooth conduction of every session. I also extend our sincere thanks to the media personnel for their coverage and for helping communicate the essence of this conference to the broader audience. A sincere thanks goes to all the author delegates, researchers who are presenting their research work during this conference. Your valuable contribution add great academic strength to the ICETET SIP-25 and help push the boundaries of knowledge. Thank you. Thank you. Thank you very much.
Thank you, sir. As we have come to the end of the inaugural ceremony, let's rise and recite national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तव शुभ नामे जागे तव शुभाशिष मागे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
We request all the faculties and delegates to enjoy a refreshing tea break just right after this, outside this hall. And the much awaited keynote session by Dr. Sibiraj Pillai on the title Navigating Bit by Bit, Realizing Cheaper GPS Receivers will start after this 10 minutes short break. Thank you all for joining us on this inaugural ceremony.
यांना gift घेतलं आमच्या वगैरे सर्व आहे ना. मग आता काही नाही करणार.
Otherwise, if you have a हाँ
इसमें ज्यादा कंफर्टेबल है
नो व्हाटएवर ये आपका जो भी है ना तो उधर ही ठीक है इधर ही ठीक है हाँ
उधर ही खड़े रहने के लिए चाहिए उनको।
तो लैपटॉप मुझे इधर लाओ इसको very good. Yeah,
Check, 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 check. 1, 2, check.
ठीक है. Hello. Hello. Yeah.
Guests, faculty members, delegates, and dear students. It is with immense honor and great pleasure I, Sheetal Mungre, take this opportunity to introduce our keynote speaker, Dr. Sibiraj Pillai, sir, Professor, from the Department of Electrical Engineering, IIT Bombay, for the first keynote session on 12th International Conference on Emerging Trends in Engineering and Technology, Signal and Information Processing, ICETET SIP 2025. Dr. Pillai sir is highly accomplished academician and an esteemed researcher in the domain of computer science and communication. His academic journey is both impressive and inspiring. He earned his PhD from EPFL University, Switzerland in the year 2007, completed a postgraduate diploma in communication system from EPFL University, Switzerland in 2002, and hold MTech degree from IIT Bombay in the year 2000. With a testament to bring his strong academic foundation and commitment to excellence. Dr. Pillai sir academic contributions are notable with over 129 plus citations, more than 19 plus research articles published in reputed journals, and 24 plus conference paper and book chapter to his credit. We are very indeed privileged to have him us today, and it is our honor to gain from his expertise. With great respect, I invite Dr. Sibirat Pillai sir to take the stage and deliver his keynote address. Thank you, sir, for gracing us with your presence. I kindly request you to begin with your keynote session, sir.
Okay, I got. Okay, good morning, everyone. Thank you for attending this session. Thanks for the introduction. I have an hour, no? That's I have an hour. Okay, so the topic that I am going to talk today is here. Okay, it showed there, but now it jumped here. I hope it's visible to all of you. Otherwise, you can come forward. I won't bite. You can come forward. It'll be good if you can ask questions, whatever you're not clear about, etc. Because the purpose is not to splash a lot of things, but to show something that we are doing. So if you're interested in knowing more or learning more or doing things there, I can suggest many things on that topic. Okay. And we have built some expertise on this based on the need, in particular, with our Indian satellite constellations up there, trying to navigate things. So let me, without much ado, let me get into the topic here. Hope that has not come back. Okay, fine. It's like our Indian satellites. Many of them are not operational, and we still, I think it's a loose connection. Okay, so what satellite navigation? I will talk in a way that the hard part of the talk, there is a lot of math equations. And that's the nature of things that what we do. And I'm not afraid to tell you that there are a lot of math equations. And you should not be afraid to seeing math equations and feeling like electric shocks or something like that. Absolutely no need. That's the very nature of things nowadays. The math is what goes directly into the chip. And this is a testament to that kind of activities we are doing. So satellite navigation is so common now that wherever you are under the coverage of some kind of a satellite. So if you look at it, like satellite sometimes puts you in the river instead of the road, and you use Google Map to land somewhere else, and all these things are now very, very common. We are so much reliant on that. In fact, this whole constellation of 30 satellites plus just for GPS, and there is another, let's say, couple of dozens coming from China, USSR, and Russia, and all the other places, Europe. So all of them continuously help us. And for even small places like inside a shopping mall, you get into a place, now we put the Google map there, and we try to. It's that kind of precision we are talking about. And the precision has not only gone to that places, but now we are using it for precision agriculture, how to see how far the plants have grown, to cut tomato plants, we use positioning systems, etc. So we have made it into that kind of ubiquitous everywhere in an industrial mass scale also. The problem with such things is that, look, you can put a very costly GPS device into your car, costs you a few thousand rupees upwards. But whereas when it comes to large number of such devices being put, you should have the cost like coming under 100 rupees to give you an estimate, or $1 in the US terms, right? I hope dollar is not growing faster than that with the recent fiascos, but 100 rupees devices we have to make and then put it into all these farms and places like that. That's kind of the outlook that we are into. But there are challenges. And turns out that these challenges that we see in 2025, the solution starts from 200 years back. And that's the way the talk proceeds also. You will see something very, very modern as you see currently, but I'll take it all the way back, let's say 200 years back to Fourier. This is the Fourier analysis, the key to solve again. I think, Robert, I'm touching it. So you can. Yeah. Okay. Good. Yeah. Sorry. Now I'll try to avoid touching that. Okay. So Fourier theory, this is 1822. That's almost 200 years back. The fellow came up with something which changed the existing French philosophy itself of how to solve problems of this. Many of you are familiar with that, but I will give you some kind of an introduction to Fourier theory also, so that you understand what it is. And then I'll get to the main problem, and the solution is where the maths and all the things come. And if the audience is not to that, then I'll skip the solutions. I'll rather tell you what the problems is. Those itself is very interesting. Okay, so what's Fourier theory? The Fourier theory is given by essentially these two integral expressions. You might have all used it in your exams and other places. So there are two integrals, very beautiful. There is a very symmetric way of going from a signal xt to its frequency domain and vice versa. They are very, very symmetric, except for a plus minus in this picture, largely symmetric set of equations. And this is called the Fourier transform. It has a profound impact on the problems that on the satellite communication, and no matter that, but any other scheme of communication that you have, right? And we can trace something back to the Fourier's analysis of things. And essentially, if you look at this, what it is, you have, there it's gone. So this camera is working. Or is it working? Because I think that the vision may be occluded by this camera from the side. But essentially what it is that like a microscope, you have to look at a signal and find out, microscopes will find the wiggly bacteria, whereas here the Fourier transform will kind of tell you what are the sinusoidal components inside the thing. So essentially it is looking at some kind of wiggles, but with respect to sinusoids. For those who are interested, Fourier had something more. What Fourier said is that time-limited signals will only have certain frequencies. It may not have all the frequencies inside the thing, right? And sometimes this may be a little hard to digest. Actually, I had written a small code just to show you. Just let me see, I have it here or not. Oh, I might have forgotten where I have put this. Okay, so let me just run this. So let me just make it bigger so that you can see it. Okay, so this itself is a good thing to visualize. If you don't understand Fourier's analysis, this is a way to see some of these things. And in fact, one of the first problems that he solved is that suppose you have a string which is attached to 2 points like this, and you pluck it to a height, certain height h, right? So the question is that you have a string which is nailed to 2 places and you pull it up to a certain height. Just imagine a guitar string. You have a guitar string attached to 2 points, you are kind of giving it a pluck and let it go. How will it vibrate? This question is what Fourier has asked. You can come sit here. There are here. Oh, yeah. So this question he has asked 200 years back, and there were conflicting answers to the question. So Fourier came up with an answer, and I have converted the answer to a Python code just so that you can see. So the question clear. The blue is the string which is attached upwards, and the red is just the baseline. So if I let it go, suppose I let it go. Now you can see how it vibrates. It's a Python simulation, but it's exactly what it will do. You can see that the string will go up, down, like that. It will keep going up and down. If there is no friction, if there is air friction, it will damp down. But what is so much in this theory? If you look at this, he was correctly able to predict this and how it moves without even doing and watching with a microscope or anything like that. But he was able to do it. And you can go inside and see what is happening is, if you look at a point in the string, so I can just go and look at a point in the string. So if you look at this point in the string, it will come here and make a lot of these little wiggles up there. And what Fourier was saying that all the wiggles, because you have tied at 2 points, it only has to be integral multiples of something which can, some sinusoids which can reside inside if you tie a nail to the 2 sides. Because if you cannot have a half sinusoid there because you have to tie it to the nail. Right? The nail should end at those points. So only multiples of those frequencies will be present inside the system. And using this here, if you look at the simulation, you will see that all these wiggles which are happening inside is exactly multiples of that length. This is the Fourier's theory. If you have questions, I'll take it. Otherwise, I'll continue. And then he also told ways about how to calculate how much sinusoids are there. And this is a very simple first problem number 1 in Fourier theory is that there's a function like that, and you calculate the Fourier transform. And then if you look at a certain interval, then you can calculate the Fourier series coefficient. You can fit cosines and sines inside. And and then you can use the transform to calculate. So we not only know that there are only sinusoids, we have a very simple mechanism to find out how much each sinusoid is present inside the system. This is a larger picture of Fourier theory, right? So any signal can be broken down into sum of sinusoids. And if it is limited in time, then there are only specific sinusoids. You don't have to look at all frequencies. Only certain fundamentals and harmonics are present inside the system. That's the key thing that I want you to take, that high-level understanding of things. If you look at a signal, it can be broken down into certain set of frequencies, and in terms of that. Very powerful tool. Many things work, or actually including your MRIs and all the things, use this as the basis of their development. Okay. Now I'm getting back to the problem. So essentially, any signal that we said can be expanded in terms of cos or sine waveforms. That's essentially the idea. And so the outline of the talk I'll now talk about the basic principles of GPS. And I'll pose a problem. What's cheap about GPS, or how do we want to make it cheaper? And what are the things we should do so that we can have like 100 rupees or 10 rupees GPS devices? And the key problem I will identify as what is called carrier synchronization. You have to exactly track the satellite's frequency and then match with it. That's where the problem is. There are other set of problems. I will not talk about it because those are much more involved than the first set. So I'll largely come to 3 of these items here. Focusing on the first 3. Okay. So even if you don't follow all the math development, at least if you know the first 2 topics, and Keynote's purpose is served. Okay, that's the thing. Let's continue. Any questions? Feel free to air. Why are we talking about it? You can ask. No problem also. Just because I know a little bit of it. That's it. No, actually, it's quite interesting. It's quite useful also. Okay. So what is GPS and trajectory tracking? What we're talking about? So imagine a projectile. So I used the base as Pune here, but of course I could set it wherever I want. Imagine somebody like a driving test, a rocket or a missile or a drone. You can think nowadays we are talking about drones. So a drone takes the shape of an 8 like that. And then drone has a GPS fit inside. And these are the coordinates marked by the drone as it flies on a thing. So this is a 5-minute run we have done. And so the speed is close to sound speed, like around 950 kilometers per hour. So it's a very quick turn of around 100 kilometers in 5 minutes that it is doing. And it uses GPS. GPS has 10 plus satellites in the view, actually 30 satellites, but on one side of the Earth and on one cone of the Earth, you have roughly 10 satellites that you can visualize. Over the ocean and other places, there are much less. Like you can see from that one of the aeroplanes which disappeared, etc. So those places there are GPS coverage is very low. Near continents, it's quite high. And the underlying technology is what is called CDM. It's code division multiple access. I'll tell a little bit about that so that you get a feel of it, but I'll not dive to details. Anybody who is interested in knowing up to some level of detail, you contact me after the talk. I can explain to you all the things, what is happening inside. Okay. In simple terms, I can explain. That's why I'm asking you, we can come back later. I'll explain. Okay, so the picture is clear. A projectile is moving like that, and that's the GPS coordinate that it is getting. Actually, it is a costly GPS device. In fact, we are using a software radio, which actually cost a few lakhs of rupees to do this experiment there. But we can do it with your mobile phone, Android phones. Apple seems to be a little more smarter. But if you have an Android phone, we can make you do the same. If you somehow put yourself on a phone and a drone, and that's how it will show. Okay. Clear. So the idea here is that you are at the visibility of 4 different satellites at least. And then from these 4 satellites, you are able to find the exact position that you are in. That's the essential idea of GPS. Here is in math, but it's in high school math, not more than that. There are 4 satellites. Of course, you have more, you can use it, but you need not use it also. You need 4, A, B, C, D. Each satellite is at position, let's say alpha 1, alpha 2, alpha 3, and beta 1, beta 2, beta 3, like that. So the positions are all X, Y, Z coordinates. The receiver is at X, Y, Z. Then we can calculate the distances from the satellites by simple geometry. Okay, distance of a vector we can just find. So 4 distances we will get. From that we have to solve for X, Y, Z, and then we also have a local time to solve. That's why we have 4 equations, very, very simple equations only that you have to solve. Okay. Once you solve that, you know what X, Y, Z is. But if you are careful, you should see that, look, I should also know alpha 1, alpha 2, alpha 3, where the satellite is. Only then I'll be able to find the distance of the thing. But that's where the GPS magic is. GPS sends where it is. The satellite sends to you, at this time, I was at alpha 1, alpha 2, alpha 3. So once I receive the data from the satellite, I'll be able to figure out exactly where the satellite was at that point of time. Right? And then I can solve these equations. And the satellites have a very, very sharp common clock. It's an atomic cesium clock. Very difficult to maintain, but for GPS, there is a cesium clock which is being maintained. And so every satellite is sharp to the nanosecond. Roughly, let's say a few nanoseconds. It's very sharp to that. And so everybody transmits at the same time. I receive. From the data, I figure out where the satellites were at that time. And then I solve for this X, Y, Z and local time. There is another big advantage is that even a very cheap clock can now get a very sharp local time, because you can match yourself to the GPS time. And that is very, very powerful actually. It is actually used in many of this experiments, LEGOs, and if you heard about this astronomic experiments, etc. You have to keep sharp time. Everywhere time should be synchronized. You're listening in Brazil or you're listening in India or China, the time has to be synchronized. And this is one way to actually get a very sharp time also. It's used in a lot of applications, including networks finding, sorry about that. Okay, so that's the basic formula, just a distance calculation formula, and then you calculate your place. Now, if it is that simple, I can tell you something that we can do very sinister with it. In fact, we have tried that. We can spoof this complete system in our local lab and create a GPS transmission entirely on its own. So for example, if you walk into our lab here, we have a radio transmitter which is doing the job of the satellites. And any place in the world you want, you open your Android phone, we will put you there. In a way that you can be completely spoofed. If you trust the Android phone, we can make you walk into some trap. Right? So this can be completely done. It is not new. We are not the only guys who are doing it. If you look at, there was an advisory from DGC, the Director General of Civil Aviation, saying that GPS should not be used if you are over the Middle East. Because this Iran and Russian-Ukraine wars, etc. happened, a lot of people try to spoof. So they send artificial signals, you listen to it, you figure you will go the wrong way. Right? And that also says why we should have indigenous stuff and why we should actually understand how it works so that we can build anti-spoof mechanisms. One part of what we do is to look at such mechanisms. Can we actually make this anti-spoof? Can we detect where things do not work? But surprisingly, this easy that you can do locally. But not everywhere though. For example, the Apple phones come up with very, very smart features that you try to fool it, it kind of bites back. Right? So Android, we were successful. Google Maps, etc. we can do that. But nowadays, things are also getting much more smarter. So we need more sophistication. But people who are inclined to do that, let me say like a Chinese lab which wants to do it, can do it. Right? So that is the nature of things. So we should understand that there are a lot of issues inside. So this is a local one. So I will explain how these things, all these things we made to work. So essentially the principle is that there are the satellites which are roughly 30,000 kilometers up in the air, right? So it's in the medium Earth orbits. So if you look at 30,000 kilometers, a signal sent at, let's say, a few watts will be nothing in the ground because it has to come through 30,000 kilometers. So even if you apply the inverse square law, you will see that it's very, very feeble nanowatts of energy coming to, power coming to you, and you're trying to detect it. So first it may look like it's completely infeasible, right? But then you should remember that we are now communicating from near Saturn. Our Voyager missions, our in the sense NASA's Voyager missions are communicating near Saturn. So it's not 36,000, it's 10 times or 20 times that we are communicating. Of course, we can. So the technology behind that. So the signals are very much, it's like, you are in an ocean. These are the signals that you are trying to rescue. The huge ocean and a few people here and there. And that's how the signals reach there on the ground. But turns out that if you use CDMA, that's a clever repetition scheme. So imagine that instead of humans, we have monkeys, and each of these monkeys have a very long tail. And they are all drowning in a swimming pool. Is it better to have humans or monkeys? If you just take a rake, the garden rake, and just pull it through your swimming pool, the long tails will attach to the rake. And like spaghetti, you can pull it out. Right? That's exactly the strategy of CDMA. A signal is stretched, you create long tails such that with a rake, you can pull it out and it will attach to itself like that. So that's essentially the idea. And for any scheme where you have low power, where you don't have so much power, then you end up using this technology of CDMA. It can give you power boost by creating long tails. So think of spaghetti that you can pull, and Each satellite will put a different colored spaghetti so that you can then pull out the spaghetti and realize, oh, this is from satellite 1, this is from satellite 2, etc., etc. And that's the technology of CDMA that's being used in all satellite communication. And then once you have a signal like that, then the actual model is a collection of all that signals. So satellite 1, satellite 2, etc. There are tens of satellites. You put them all together to create a superposition. So it's like a pasta with a lot of things that put together and given to you. You have to figure out the individual satellite signals to find the positions of the satellites. But the unfortunate part is that the satellites are moving over the atmosphere at a very fast pace. In fact, much higher speed than the local cars or the aeroplanes, etc. And there will be huge Doppler effects because of that. The frequency that is sent from the satellite is not what we receive, because satellite is essentially slinging past the atmosphere at a very high speed, because these are not fixed Earth orbits. These are medium Earth orbits where you do not rotate with the Earth, you rotate at a much different speed, right? And that's a problem. Otherwise, if you don't move it faster, what will happen if you don't move it faster? The gravity will pull it in, right? It's centripetal force and your Newton's laws which will do that. You have to sling faster, but faster means there will be a lot of Doppler. So there will be a lot of frequencies, new frequencies, which will contain inside this. And then there will also be attenuations and delays from the satellite to the Earth and so on. So the signal is corrupted by a lot of things. In addition, there will be a huge amount of noise due to the circuitry that we are using. So this is a challenging problem. To get this done is really a challenging problem. So many satellites, so many Doppler speeds, so many delays, and huge noise in the system. Essentially, if you take an oscilloscope, look at the signal, and if I switch off the signal, you will not be able to say anything. Signal is there or not, you cannot say by looking at that signal. So what is the solution? You have a signal, but you don't even know whether the signal is there or it's just plain noise. What is the solution? Increase SNR is good, but we are limited by the solar panels that is providing to the satellite. And 30,000 kilometers you have to push through. No matter what power you're trying, it's not going to, the transmit ideas won't help you at all. Unless you start putting a hydrogen bomb and now in the satellites, and there are hydrogen capsules they are building, right? And then pump a lot of power down there. Otherwise, not a bomb, but a battery, and then do that. But that's not being done. So you face this problem not just here, but if you go to, for example, even under an MRI machine, if you take the signals, first time signals or the ECG machine, it is corrupted by large amount of noise. But you are seeing the signal which is cleaned up, filtered and processed so that you don't feel like you are seeing the noise. But here it's much more worse. So any suggestion as electronics engineers? Yeah. Key matching. It's a start. It's a good thinking start. But then what's the key? Good, very good. Think like that. What he says is called pilot signals, that you know something, so then you try to match this. Like I want to identify, am I in the correct class? I know a few people, so I'll say, this is the correct class because I know the other people. Yeah, you have a question, please. Oh, if you reduce, the problem is that if you tie a stone to a string and then you want to rotate that, what will happen if you reduce the speed of it? It will not do the sling. So you need to have a certain speed to get the mv square by r to balance out the thing. Otherwise, it will come a problem. In fact, that explains the collapse of stars and other things also. When you spin, when you don't spin fast enough, you collapse. Yeah. The question is that this signal here is corrupted by a whole lot of stuff, noise and other things like I was showing in this picture. Oh, sorry, where is it? Like here, it's corrupted by a whole lot of them. If you look at the oscilloscope and the signals coming by, you will not even know the signal is there or not. If I switch off the signal, nobody will notice. It was that much low it is inside thing. So what are the techniques available to you as engineers? Suppose you see such a signal, like an audio signal corrupted by a lot of noise. What will you do as an engineer? Good. But filtering means that I have some idea what to filter. And that is where the Fourier and the wavelet and those analysis and the theory is going to help you. Now, if you look at filter is a convolution, but to look at a signal, what you can do is that you can look at the transforms of the signal. What frequencies are showing up, you can check. So a sinusoid buried in noise will not appear as a sinusoid in your time signal. But the moment you do a Fourier analysis, it will show a sharp spike at that frequency there. That's why the importance of Fourier analysis. There are similar tools in wavelet analysis, time frequency analysis, etc. The whole signal processing evolves around such things. Your JPEGs, your MPEGs, all these things work using this basic idea that I'm talking about, that there is a way to look at it. Once you look at and figure out, then you can apply what he says. We look for some matching components in the system, and the matching is actually provided by this long tails I was talking about that provides what to look for in the signals. Okay, so the Fourier analysis or the frequency analysis is first tool you should apply on any signal if nothing is clear, visible. If you're seeing a sinusoid in front of you, good, no problem. But if you don't see, you see some very corrupted signal, put it to the frequency analysis first. Okay, that's like an engineer's toolbox. First item should be Fourier analysis. Please. Yeah. Correct. Okay, so that's the challenge. And how do we solve this problem? Unfortunately, we do what he says, but in a very brute force way. We take all possible Dopplers, all possible delays, and then create signals and then try to compare. Right? Because if the satellite is at a certain speed, this will how the signal look like. If it's a different speed, this will be a different signal. I try to match with each of them and figure out where the thing is. So essentially, it is like finding this lock. You take brute force, try all the thing, break the lock open, or try all the combinations of the keys till it works. That's how we do in our systems here. Now, because of this Wi-Fi's and wireless systems, etc., we do a little smarter. We know where to start and end. We have what's called an almanac, which lists what are the satellites present at the time of the day and what will be their speeds if you are at a certain place. So we know roughly where they are, but still we need to search. It's like telling you that your code is between, let's say, 500 and 600. Then you start from 501, 502, 503, where the code will open, the lock will open. So it's a bit course again in this thing. And that's where the things get very costly. We need processing power. We need to find where the signals are. We need to search, and we need samples collected at a fast enough pace, etc. And that's why we cannot simply get very cheap devices built for that, because we need to do all these operations to figure out. It's a brute force search we have to do. So here is a brute force search, how we will find for a particular satellite. So for each Doppler, you try to search whether the signal matches that speed or not. And then every time delay you search, and you search through all this rectangle, and then there is some place you find a match. It's like looking for the correct head among the set of people that we have to do. But we have to search in frequency, search in time, and figure out where the job is. A tough job. It's where the pain of the effort goes into the. Okay, so that's the signal up here. And how did we do it in the lab? In the lab, we did not build, of course, we built all this from scratch also, but later we realized that there are actually fantastic open source libraries can do the complete job for us. And here is one software that you can actually play and the experiment. This is called GNSS-SDR. It's built by the European Union, Spain, for the European Union satellite. A complete open source, entire code, everything is available. You can just download and start using it. So we also started using it. And this is all the things that I show is using this tool here. And the tool is powerful. What it requires is that you have to have a hardware device which takes the input and then gives you samples. So it gives samples at a sufficient speed. Then the rest of the processing can be done in this picture. Right? And so we looked at it and said, okay, what is the costliest component? How can we reduce the cost down here? The cost is not software zero, near zero, I mean, whatever it is. The cost is on the hardware, and the hardware which samples and gives you at a certain speed. That's where the cost of the thing is. And then the cost is on the processor, which tries to figure out what the matching is. Hardware is the biggest cost there, and then the processor, again hardware, but you can think of as software also, is a chip that you're using, and that's where the cost of the thing is. So when did we start? 11:30. Okay, I just want to keep some idea of the time, otherwise I'll just go on and you will get bored. Okay, so so we said, okay, how can we save the cost of the things? Any ideas? How do we save the cost? So the biggest cost in many of these devices is what's called the ADC, the analog to digital converter. If you go for a high precision, like standard 12 to 14 bits per sample at a speed of 2 megasamples per second, etc., or 2 megahertz, it is costly. Analog devices sell something for like $500 or maybe $100, like thousands of rupees if you want to buy those things. I may not be correct in the cost because I'm maybe talking the cost of the board, but the chip may be cheaper. You just buy the chip. I'm talking of the board. Okay. So, but again, this is a costly item. So we tried, okay, what can we do? So now watch out. What we did is we collected samples as in the previous experiment. And what we did was for every sample, we just threw everything out other than just the sign of the sample. The signal is plus or minus. If it's plus, I'll say 1. If it's minus, I'll say 0, or vice versa, one of that. Right? You just take is it plus 1 or minus 1? And then we will run the experiment again. Look at the huge cost savings that we have done. Instead of all the ADCs, all we need is what's called a simple comparator. If you have an op-amp, you can build it very easily. The signal is above 0, you output 1. Otherwise, you output minus 1 or 0. As simple as that. Okay? So we went and matched this to a very simple mechanism. I'll show you how the output shows like. So what I do is that we can actually show all this output on a local computer. So let me just put this running into a local host. We can make it work anywhere in the world because the maps are available for anywhere. I have chosen Pune, the same experiment as we had before. Okay, and so let me now show this. This is, I should not run because I need map to download maps. I need internet, but it's okay. I'll show it here. One step is okay. Now I'll run the receptions, but with just, let me just run this. I'm running it very fast so that you can see it quickly. So if everything is correct, you will see the same pattern traced as the 8 pattern that I have shown there. So I'm going to run the thing. This is the correct one. Yeah. You can see that it is doing the exact pattern as we had before, except that I have only used the signs of the samples. This run, I use only the signs of the samples. I'm not using the values of the signal. And I don't have to store that much now because my saving is 14 times less. Instead of 14-bit ADC, I'm using 1-bit ADC. And then 1-bit ADCs are dirt cheap because comparators and things like that. In fact, even a few rupees, 1, 2 rupees, you can build a comparator and an output for that. Processing cost, I'm not deducting. It is there in the computer. But the initial cost itself can be coming down by huge amounts if you just simply make it work. Unfortunately, it's not connected to the net. Otherwise, the map may not download. Oh, it's there. Then it's okay. Okay, it looks like the map is there. So you can see it's the same thing. Almost no loss, except that in the beginning, it takes a little more time to track it. But rest of the, once it gets it, it continues to do that. So our idea, throw away all that extras of hardware and associated things, just 1-bit comparator into the thing. It becomes dirt cheap to start with. The hardware, except the computer part, becomes very, very cheap. But then the question, that's where the question started. What, all the signals, all the satellites, with 1 bit per sample, you're able to figure out everything. Is there something wrong? Does the theory permit this? Right? And that's where as I said, the theory takes over, and you want to try to explain things and see that if it works. So we said, okay, let's develop the theory to look at it and see if it really works or not. And the rest of the theory is, I have to go back to the slide. Yeah, the rest of the theory. So here is what we have. With 1-bit quantization, we are able to get nearly there. All we are using is just signs of the samples, and we are there. So we can make it cheaper and cheaper. And we wanted to understand why it is the case, and that calls for a PhD student to work. So luckily we had Anil Yadav, a PhD student with me. So we said, okay, let's look at this problem and see how we can answer. Can we at least convince ourselves that things work? And the main problem, as I said, is how to find the frequencies, how to find the Doppler coming from a satellite. So what we did was, instead of looking at a complicated system, we started with a very simple model. Suppose you have a simple carrier, and that carrier has a carrier frequency, but there is a Doppler also, and there is noise, and there is a phase, and you only get the sign of the signal. Just to illustrate, here is a signal. If this is a signal, then you only get this rectangle signal, which is a sign of the signal that's given to you. And from this, we have to figure out what is this Doppler and what is this phase theta. There are 2 parameters to be figured out in this problem. And we are taking not this signal, but just a waveform. If we can make it work there, then we can think of making it work for more complicated systems. Otherwise, if we cannot even get it working for this simple system, then of course our experiments are wrong. There is something wrong with that. Okay, we should figure it out. That was our thought process. And in sampled, you will get whatever that instead of continuous time, you get sample instance n, which is in that system. So that's the base model. There is a lot of noise. There is a waveform, which is a standard cosine waveform or a sinusoid. And then I'm interested in finding these 2 parameters, the Doppler and the theta. Let me just stop for a quick second and ask if there are any questions related to what we discussed or related to this problem. Because if you understand this problem, that's how we solve big problems. We kind of abstract them to very simple primitives that we can look at it and appreciate, then come up with answers, and then see if we can put it back to the more complicated problem. Okay, so feel free to ask any question related to this, why we are doing it, or even, please. Yes. Exactly. See, once we get that frequency correctly and the theta, that phase also correctly, then we know what signal to search for. Because now we have identified how the person will look, because we have photo now, because we know the correct photo. And then we'll go and match whatever the satellite comes with the correct frequencies. Then we will be able to figure out the data contained inside it. Once we get the data, we'll know the position of the satellite. And then we can solve for 4 equations. Yes, yes. All this, yeah, correct. That's all there. So RF signal, what we get is 1.575 gigs. That's the GPS standard frequency which is coming. And you can think of the IF we are talking about, this FC, this IF is around 6 megs, 6 megahertz or 10 megahertz. Yeah. Yeah. So RF into RF is you can buy a standard receiving plug, right? And just put it with an antenna, and it will start feeding the signal at the IF for you. And then you sample it, right? And then that's where the cost now comes into the picture, right? The sampler, the ADC is costly. Huh? Yes, sir. Yeah. Yes. Yeah. So except that we don't want to eliminate in the Doppler. See, what happens is that a siren is let's say an ambulance going on, and we are hearing the siren. We don't want to eliminate it. We want to appropriately put it back, and so that we hear the correct frequency. We have to, yes, exactly. So that's the wipe off that I'm talking about. The Doppler, once I understand, then I know what I should expect. Carrier frequency is on top of it. Correct. So once the Doppler is with me, then I know what it will look like, and then I can compare and get the data. That's the idea, right? Essentially, like Doppler carries information in the following way. Something is speeding. Absolutely, right? So that's what the strength of it is. If you know something, you can always make the connection, right, and visualize. And that's a good way to understand these problems. Whatever you know logically or real life experience, just try to match to that and see what is the connection. And ask questions, of course. Just stay silent, you will not get it. You have to ask questions. Okay? Right or wrong, there are no right or wrong questions. Wrong questions can also be asked. But once you answer it correctly, your know-how goes up. Any questions? Last, etc. are very silent. You don't have any questions or? Please. We are getting that sequence from which we have to figure out what is that FD and theta. That's a challenge. Okay, but the biggest problem is a lot of noise there, which will corrupt the signal. So now you'll see why I was talking about Fourier analysis. Sorry, talking about Fourier analysis. So whatever the continuing change of phase, I have called it as the FD. So there is a phase varying component. So I'll abstract it into the frequency, and the fixed phase offset, I call it theta. Both are important because we are talking about nanoseconds time differences. So I need to get not just the frequency, but also I should get the phase. Otherwise, I'll make mistakes of the order of hundreds of meters. Right? Our precision, we are talking about 20 meter. That's the kind of thing we want in GPS. Right? GPS guarantees 50, but with a lot of extra, we need like 20 meters or 10 meters. Like if you're on the left side of the road, we should not put you on the right side of the road. So that's the 10 meters or 20 meters we are talking about. So we need that. For that, the phase is very important. We need to get both. Okay, so now that's where the challenge here is a 1 bit of the output, like here last slide here. This 1 bit output is coming to you. In fact, samples of that. And to make things cheaper, we also make a 1 bit local oscillator. Now 1 bit local oscillator is very easy. Like 0, 1 signal. If you want a sinusoid, now you have to come up with filters and more complicated things. But 1 bit of this local oscillator, and then you accumulate those values and you get this output I. This I called as an in-phase component. So you make a measurement after listening to n samples, you accumulate and you put out one value. So this is what our receiver will do. There are zeros and ones, or ones and minus one coming. We have ones and minus one locally generated, multiply them, add them up, and take an average and put them out as the output. A very simple operation to do, but at this point we have a real value to look at. Now you can also do what's called the Q component in communication, where instead of a cos, I dot product with a sign. So the cos and a sine, they give some extra information to each other. So I have two values, I and Q, from which I have to figure out what the value of FD and theta are. Right, that's the question. And apparently some work has been done on these problems in the 2008 in China and the US. They looked at the problem of finding if there is no frequency offset but only a phase offset, how do you find it? Turns out there the problem is not difficult, because what you get is a rectangle of this form. Suppose there is no noise, so you get a rectangle of this form. You don't know where the theta is, how much you are phase offset. So you just start searching, right, where it exactly aligns one on top of the other. Like imagine you have a sequence of 1 zeros, 1 0 1 0 1 0, something like that. If you align on top of it, then you will see everything will match and you get a good output, like a photo matching. So what happens is that if you are away, if you are not aligned, then your equation will look like this. The more you are away, the less it will be. So it will, the amount of correlation, amount of match will taper down, right? And this is the problem, right? And so at the correct point, you actually get a lot of high correlation and the value will be close to 1. So our I value will be close to 1. The picture, I'll draw a picture in a minute. But this is the answer for FD equal to 0. And this is done by Chang et al. And there are some US patent granted on such developments, etc. But when FD is not 0, there are people looked at it. In fact, these are like well-known groups in the world, Germany and US, who actually look at such problems. In this area, Gerald Fetway is a very prolific figure in this area, very authentic figure. So they have looked at these problems and they have come up with what's called oversample. If you make a lot of samples, tens of 20 extra samples per period, then you will be able to guess correctly. So instead of just looking at the sign of a value, you create more and more samples and then decide, which makes sense because you have a sequence of ones coming and you can look at it several times, then you can make a better guess it's 1 or minus 1. Essentially, that's the idea. But 20 times oversampling is proposed by these people. Whereas due to the importance, there are others who actually came up with lookup table based implementation. If you receive a certain set of values, then you should predict that it is a frequency, Doppler is so much and so forth. So these are lookup table techniques. So these are practical techniques, but unfortunately very, very costly to implement on the cheap device that we are talking about. That's where we came up with an answer. So this is how the correlations will decay if you have FD equal to 0. So there's a picture which says that if you are matching correctly on 0, then you will have a high peak, otherwise you will go down. And using this, you can figure out what the theta is. Okay, now it's our work, and here it actually is a little math. In fact, I'll use the to good Fourier analysis to good use. So we had to find FD and theta from this I and Q values. And our approach is very strange. We'll complicate things pretty much using what's called Fourier analysis. And then we'll start looking for solutions in this complication. So it's like somebody has given us a masala, we kind of add more oil to it and mix it up and mash it so that it looks very ugly. And then we will start to taste it and make things interesting. That's the idea. So what we do is that, that we have the I value, which is nothing but a summation, which is an accumulation. We go back and write it as an integral. That's doesn't make much difference. It's a summation or an integral. And so we keep the continuous wave, and the summation is approximated by this integral just for the purpose of theory. But once you have a continuous waveform, this is a square wave. And of course, square wave has a Fourier series. I said it can be written as sines and cosines by Fourier analysis. So I write this as a correct set of cosines of this form. And my incoming waveform is also 1 bit quantized. So which means it's another square wave. In the absence of noise, I can also write it as another sum. So both are sums of sinusoids. But then together there's a double sum. It becomes very complicated, looks like that. But from this complicated thing, I had to figure out the red points, FD and theta. right? And so we first said, okay, it's complicated, but what will happen if FD is 0? We already know the results from the previous work. Can we get the answer when FD equal to 0? Look at what happens when FD is equal to 0. This is cos A, cos B. Or simple trigonometric identity is cos A, cos B. So you'll get a component cos A plus B, you get a component cos A minus B. And if you look at the cos A minus B component, if FD is 0, then the FCs they kind of work on each other, get out of the picture, and you can kind of target the theta there. That's the idea. And turns out that if you correctly identify the correct sums here, the good terms are of this form. Everything else is of the form 1 by FC. FC is the carrier frequency. We are talking about tens of megahertz. And you have some number divided by tens of megahertz, which is almost negligible compared to the first term. So that's the crucial intake from all these things. We are able to figure out what is important to us, and we are able to throw away what is not important to us. Whereas previous works tried to get all of them into one number. So they wanted exact formulas to work. Because of that, things were not working. What we did was we did not make exact formulas, but the relevant terms we pulled out and put it into a sum. Now it turns out that if you understand Fourier theory, then there is a way to actually write it as a function. Again, it's an inverse Fourier series. And it turns out that this number here is a very simple formula, exactly matching the formula of the previous work. So we get the formula which is same as the formula derived in the previous work, but we used a completely different way of coming together. And that is for the case when FD is equal to 0. Oh, so we were buoyed. Okay, good. I mean, this is a way to look at it. So now can we work the same thing for non-zero Dopplers? So the math becomes heavy, but turns out that it requires several weeks of work. And in fact, my student Anil and I, we were sitting together and trying to scratch out each point in a long sheets of papers. Turns out that we can actually write it in a very simple form like that, plus all the other terms which are not important, you can throw it out. This is all part of, I'll mention the publications at the end, so you can get all the formulas there from the paper. And turns out this also has a very nice Fourier expansion, and you get a very simple function. In fact, I'll show you the function here. This is how it will look like. Instead of linear functions, you will get polynomial functions. And suppose I show you this function and ask you to guess what will be this function. Anybody here can guess. Suppose I show you only the function, I don't tell what I plotted. Can anybody guess? I mean, at least for a moment, just take your view from the mobile phone and look at here and see. Means if you cannot even think or start to think what kind of a signal is this, then the electrical engineering thing you should be very careful about to pursue. Can you think? I want some set of answers to come forward. What kind of a signal is this? Please, others also. Yeah, this is, any guess? If I give you a signal like that and ask you to guess, this will be, I mean, any decent company working in the core will be that's first question in your campus placement. If you can answer it, of course, you will be comfortably answering there also. And the way you answer, people know whether to take you or not. Natural, it is natural. Look, you should guess that this is start of a sine wave. That there is a sine wave which comes like that and the other cycle which goes like that. Except that what I plotted is not a sine wave. What I plotted is this waveform here. It's a polynomial waveform. Right? A polynomial which looks like a sine wave is what you will get. And then naturally what you do is that, polynomial is too tough, I have to work with that. Sinusoid is something that is bread and butter for electrical engineers. If you doubt my question, just put your hand in the socket, you will see that what I talk about sine wave is true. And you get the shock of your life with the sine wave. Okay, so it turns out that if I draw a sine wave, actual sine wave pi by 2 sine phi, it will exactly look like that. So the pink is the sine wave, blue is the actual waveform that we get, but the actual waveform that we get by approximating things. So we might have lost something. Sine wave is another approximation of that waveform. But once you get a sine wave, this problem solutions becomes extremely easy, right? Because you just have to substitute this in, and the I and Q values will have plots like that, and then we can actually, I'll not do the details, but you can get answers of the form. If you make two IQ measurements from which you can easily figure out the Doppler frequency by using this formula here, where nu is 2 pi fd times the integration period. So this is related to the Doppler. One simple formula, if you can solve, you can get the Doppler. The only catch here is that you have to use tan inverse. Unfortunately, tan inverse is also not a good function for a small cheap processor to compute. So you have to have a lookup table for that. Turns out that we can even solve that problem and come up with a very simple formula. Here is a very simple formula which will find out even without the tan function by using linear approximation of the functions. So all these are parts of the paper, and we have verified this the performance of the algorithm by running through various simulations, and you can see that the Dopplers after our corrections will be of the order of a few hertz, whereas the actual Doppler is 5,000 hertz, like 5 kilohertz, 10 kilohertz, 1 kilohertz. These are the Dopplers. After our correction, we are in 1 hertz, 2 hertz, etc., which means that now we can have the small PLL loops, which will now figure out the actual frequencies. So the whole theory works out beautifully. And the remaining part, we actually put it back to the GPS just to see how things work. Turns out, now I will not go through the details here. I'll just quickly show that look, this can all be done. And turns out that we have error probabilities which are very, very low for the standard operations, like 1 in 10,000 bits, etc., going wrong, which is very easily correctable by our mechanism. So the whole system, whatever we observed, is not fluke. There is a theoretical basis and a justification, but it was not easy to see that justification. We have to take it upon ourselves to come up with the entire theory and see the end, how it applies to our thing. So it is from a practical observation, or from whatever we have observed, the theory kind of answers the whole picture and gives us the complete picture of why it works, when it will not work, etc. Because now we can answer also when it will not work. There are certain lengths that things will fail to work, etc. So this actually will help us take it further to other systems. So this is, to conclude, I was talking about the theory and practice behind phase and frequency discriminators using on-bit samples. They are good enough for low data rate applications like navigation. And currently we are trying to see whether we can apply such things to our NAVIC and the systems that India is developing, etc. How we can give theoretical justifications, and from 1 bit to 2 bits, 3 bits, etc. can we move out. All the things that I talked in today's talk is part of this paper appeared in IEEE Transactions and Communications. And Anil Kumar Yadav is the PhD student, graduated, currently working in France. And Professor Appaya is my collaborator, my colleague at IIT Bombay Electrical Department. And paper is available there. And if you have any questions regarding the talk or the paper or anything concerning those things which I know, feel free to ask, or you can send me an email. There are a lot of interesting projects related to this hardware and software that one you can try experimenting. In fact, for example, you guys all can get together and build a GPS spoofing in Raisoni some lab, and then bring people in and spoof them and show that how you can do this. So there are a lot of projects related to this that one can pursue. But the topping, you should see that it not just requires engineering, it also requires the analysis and the math to put the story together. And if you do not have the strength in both sides, you have to collaborate, and you have to get that strength. If you are very good in practice, weak in theory, still that's okay. But then you should collaborate with somebody who is good in theory. Perhaps we can practice, because then people will, as equal partners, they will actually respect the contributions, and joint developments, etc. will happen. Only yesterday, I think, or day before that, India and US together launched the NISAR satellites, right? So that's technological respect that you have certain capabilities, people come together and do that. So like that, our students also should have that kind of capabilities to collaborate and do things further. So that is why I thought this talk will be appropriate, though I knew it was a little, the math, etc., maybe a little higher for many people to follow. Don't worry if you have not followed everything, but if you got a sense of what things are inside, that itself is a purpose served for me. So I will stop, conclude here, and I'll wait any questions from you. Wait for questions.
Yes, module, size reduction in GPS module. Yes, one day. Definitely. It's
So the question is, will there be a size reduction in the GPS module? If you look at the GPS modules, they are anyway not that big in terms of physical size.
still, if you want to have the reduced size, it is possible with this.
Because I think the size, the form factor or the size, to my knowledge, largely comes from the antenna and the LNA of the RF part. That anyway stays. Because the antenna with an LNA, anyway, the bigger part, you need a bigger patch to be put there, etc. So that form factor will be there. We cannot reduce on that. Apart from that cost, but that cost is, let's say, a few hundred rupees. You can get a GPS antenna on Amazon for 200 rupees or something. Yeah, so you can get a GPS antenna for 200 rupees or something like that. But an ADC of that quality of what we have in that radio devices, etc., are quite costly. If we can just replace it by a comparator, maybe I'm picking feedback from that. If I can just replace it by a comparator, that takes no space, but compared to the antenna, anyway, it is nothing, right? But the money cost will be very good, very high. And we have our own in-house Navic receiver in IIT Bombay, and that outputs 2 bits, but currently it outputs 32 times the required sampling rate. Yeah, but that's again analog devices, it's quite costly. Right, but we want to make cheaper, means you have to just replace by the costly items. That is correct also. Yeah, but then what we can do is that we can remove this antenna as a separate module, like cars, etc. do. They put an antenna at a separate level and then it plugs to the thing. Then this module can be very, very small. That's the thing. But the money for the ADC is where we can actually save. Students, please feel free to ask.
Any question from student sides? So may I conclude here? A formal vote of thanks to Dr. Sibiraj Pillai sir for his insightful words. And I think all the researcher will work on this topic. Thank you, sir. Thank you, sir.
Kindly hand me the attendance sheets.